Yeah, it's kind of an unimaginative title, but I really couldn't think of anything else. First of all, I'm delighted to have been invited to this conference. It's proving to be a fantastic experience. Many, many thanks to Mike and all the organizers. So I'll sort of introduce the subject, and I'll follow the remit that Mike gave me, which is to say something about the complex dynamics of active systems in general, and then I'll talk about some recent work of ours, and then I'll summarize. So in slightly more detail, there's an interesting piece of prehistory in active fluids, and these subtopics is what I'll discuss here, the role of inertia, and so forth. Okay, so what is active matter? So we all study non-equilibrium systems, which are non-equilibrium as each one, as Tolstoy said, in its own way. But what they all have in common is that these are systems that are fed energy, which they dissipate, and in doing so, execute some kind of systematic movement. The idea of active matter is that you don't force it from the boundaries, you don't force it by putting on some field. You've got particles, and each particle is directly supplied with a sustained supply of free energy, which it transduces into some kind of movement. So obviously, the idea is to bring living matter into the warm embrace of condensed matter physics, and that's why this category was defined. Basically, each particle has detail balance broken at the particle level, and collections of such particles we call active matter. And as with all non-equilibrium problems, you can either write down the equations for such systems by pure unaided reason alone, or you can start from sort of standard equilibrium Langevin equation dynamics and take one variable, which is the chemical driving, and hold it in a driven state and build the equations that way. I won't do this, but it's done in various places, one of which is in an article by me a couple of years ago. So what kinds of systems are we interested in? Apart from the cell biological and subcellular systems that we heard about in previous lectures, we're interested in collections of self-propelled things on any scale, from subcellular to organisms like this to birds and so forth. I don't know why it's playing like this. But given the definition I gave you, which is that particles directly supplied with energy which they transduce to do something, you can imagine non-living realizations of active systems. For example, you can imagine, I have to go here, I think. You could imagine taking a surface and placing a particle on it and vibrating the surface up and down. So you're looking at a top view here. I have a table. I'm vibrating it up and down like this. I've put a particle on there. The particle has a funny shape, and as a result, the particle is self-propelled in the plane. So as far as the dynamics in this artificial two-dimensional world goes, it's a system which is suffused with a throughput of energy in the third direction, and its two-dimensional dynamics is that of an active system. So it's legit to call this an active system, and it's legit to use systems like this to test your ideas on active matter. There are many other realizations, some of which I think Mike mentioned, like rods propelled by chemistry. You could even imagine taking a two-dimensional, say a 2D metal or something, and placing two of its faces in contact with leads which are maintained at different thermodynamic conditions. So then again, you're pumping energy through that way. And the 2D physics of this should be some kind of active system physics, provided it's in the regime where it actually dissipates the energy. And this kind of idea has been used in understanding so-called zero resistance states in 2D electron gases and so forth. Anyway, I won't be talking about these. Obviously, the reason you should care about this is that you're trying to understand the emergent laws governing self-driven matter. You want to understand living matter as a physical material. Maybe you can imitate its functionalities. Maybe you can design clever materials. I won't really tell you about these in today's talk. I will be telling you basically about ordered phases of active systems. The simplest kinds of ordered phases you can think of are liquid crystalline phases. The particles themselves could be elongated. I don't know where is better to stand. The particles themselves could be elongated, in which case they're likely to form liquid crystalline phases. They could have a sense of front versus back. They could be apolar. They could organize into states which have a net polarity, or they could organize into aligned but non-polar states. You can also have collections of particles that don't have any particular polarity, but are still self-driven, and you can try to understand their phases. You can understand condensation, crystallization, and so forth. Active matter is a subject which is blessed with an excess of review articles. That's my favorite one, but there are many other really excellent ones, and do take a look at them. One other important thing, apart from the types of order and the types of particles, is the dynamical regime in which you operate. You can imagine collections of active particles in bulk fluid, or you can imagine collections of active particles. Here, there's a binary mixture of sheep. In 2 dimensions, it's clear that their interaction isn't being governed by modes that travel through the Earth, but rather by contact and visual interaction and so forth. Unfortunately, we adopted the terminology wet and dry to describe these systems, thereby violating Feynman's original terminology of wet and dry water. So wet and dry here means with fluid and without fluid. Okay, I told you I'd say something about prehistory. People 50 years ago were interested in the question of what is the fluid dynamics of a collection of particles that are powered. So Finlayson and Scriven actually discussed the idea. Their paper is actually called Convective Instability by Active Stress. So they invented active stress, not us, and a long time ago. And they were fully aware of what an interesting problem it is. It is like they actually issued a kind of invitation to come work on this field. They talked about motion without the intervention of outside forces. They said that the necessary engines operate in living systems. I didn't even know that people said complex fluids in 1969, but they did. These are all quotes. So they really were telling everybody to come work on it. They talked about artificial active systems by talking about polymeric and colloidal systems approximating living protoplasm. But oddly enough, this paper is almost unknown. It didn't launch, by no means did it launch the field of active matter. It doesn't even feature very prominently on their web pages, oddly enough. And I think the reason it didn't launch a big surge of movement in this direction is that the framework that we use to study these systems, namely fluctuating hydrodynamics of systems with broken symmetry, hydrodynamics beyond simple fluids, dynamical critical phenomena, none of that had appeared yet. So I think somehow it came just a few years before its time. Anyway, so that's prehistory. So let me now enter the second part of my talk, where I will tell you a little bit about the varieties of dynamics you see in active systems. And I deliberately have chosen a system which is not a fluid dynamical one and not biological. It is, you've got these little bits of metal wire, a few millimeters long, 5 millimeters long, on a vertical vibrating table. The particles are housed in a container which is slightly thicker, has a gap slightly more than 1 particle diameter. So you shake this thing up and down, and these particles shuffle back and forth. And depending on the symmetries of their shape, they do different kinds of movement. Here, we will look only at particles whose 2 ends are the same. And so what they do is they shuffle back and forth along their length. Even that is different from thermal Brownian motion. If you have a rod-like particle, and you ask about its kinetic energy, it will have as much kinetic energy this way as this way as this way. So if you think in terms of kinetic energy, these are clearly particles which are carrying maybe 2 temperatures or whatever. They're clearly out of equilibrium particles. And what they do is they form, at high enough concentration, they form what looks like a nematic phase, but for most parameter values is a rather violent nematic. So what you see is a fair amount of nematic order, and then you see topological defects rushing around. So as far as I know, this is the first instance of active nematic turbulence. It came in a non-fluid dynamical context, namely this dry 2D system. And although this turbulent state was not what excited us the most at that time, we did notice that it had topological defects in it. I think other speakers have already told you about the kinds of defects you can have in apolar systems. Their strength half or minus half according to the angle you accumulate by going around one of them. You can also have integer strength defects, which I'll come to later. And we looked at these systems and we noticed that we were looking for evidence of movement induced by curvature, and we noticed it is particularly pronounced around these defects. What you can see here is a plus half defect barreling along and a minus half defect staying put. The movie is not as convincing as a set of still photos. So you can see here that you have a plus half which slowly moves along and a minus half stays put. So we found this mildly exciting at the time, and we put a learned statement into the supplementary material saying that it's crucial for our discussion that the symmetry of the field around the strength minus half results in no net motion, whereas the curvature around the plus half has a polarity, and so it should move. So this was great fun, and this was the active pneumatic. More recently, this idea of motile defects we took up in collaboration with Suraj Shankar, Christina Marchetti, and Mark Bowick to understand the dynamics, the statistical mechanics of an active pneumatic in which there are topological defects. The idea basically is you've got defects of strength minus half and plus half. The plus halves and minus half interact with a pair force which is from a logarithmic potential, but the plus half has a self-propelled velocity. You can construct this description starting from the description of an active pneumatic, and then you can study the statistical mechanics of the system, and what you find is that even though the plus half is motile, and therefore you might expect that if you had a plus and a minus, the plus would always race off and completely destroy the pneumatic phase. What happens is somewhat more interesting. First, let me just tell you the naive picture. There's a logarithmic attractive potential, and you can think of the tendency of the plus half to run off in some direction as like a linear repulsive part. If you have a potential like this and you start a particle here, obviously it will always escape eventually with any small amount of noise. However, the point is that this picture holds only if the plus half maintains its heading all the way to the point where it reaches that maximum and escapes. So therefore, what you expect is that at high noise, they're unbound for purely thermal reasons. At low noise, they're unbound because the plus half doesn't lose its direction and keeps going and crosses the barrier. So what you expect from this is that as a function of activity and temperature, you have a melted phase at high temperature and a melted phase at low temperature for any non-zero activity, and in between you can have a pneumatic. So you have a re-entrant melting transition. So I should emphasize that this picture of the active pneumatic is rather distinct from what you've seen in the earlier talks, which has to do with the hydrodynamic instability driving a bend, hydrodynamics driving a bend instability and producing motile defects. Here the idea is if you have a defect for some reason, it is motile, and it's motile for symmetry reasons because it's got a polarity and it's out of equilibrium. So this is one story. I will not say more about this. Let me now come to active pneumatic with fluid. You saw these equations or equations like these in Luca's talk and possibly other talks. You have an orientation tensor, which is advectored, rotated, and flow aligned. It tries to relax to equilibrium in some effective free energy. You have a hydrodynamic equation, which here I've written without inertia, viscous force densities coming from thermodynamics, pressure, and one extra bit, which is a stress simply proportional to the degree of uniaxial order. So the idea here is that whereas at thermal equilibrium, a pneumatic phase with full alignment still has an isotropic pressure, an active pneumatic, simply by virtue of the fact that it has an aligned state, automatically has an aligned stress. So it has a non-zero deviatoric stress on average. Unsurprisingly, a system of that sort turns out to be unstable, as you will see. But anyway, basically, you take conventional liquid crystal hydrodynamics, you augment it by a stress proportional to the Q tensor. If you had particles, you introduce also a particle current proportional to the divergence of the Q tensor, and you can solve these equations. Rather than solving these equations, I'll just show you a cartoon. What this story just now tells you is that if you have an aligned state and you perturb it slightly, then if there are pullers, if you perturb it splay-wise, the secondary flows set up in the perturbed state tilt your orientation further in the direction which you already tilted it. If you have pushers, then instead the instability is in bend. Okay? And important things to note, this is an active system. It's characterized by a scale of stress. Given a scale of stress sigma and a viscosity eta, you can make something with units of time, which is viscosity over stress. So there's one single dominant natural time scale, which is eta over sigma. Secondly, there's a competition between the intrinsic aligning tendency from pneumatic elasticity and active stress. So there's a characteristic time scale and the characteristic length scale. And what you expect is that at length scales big compared to this, have I got it right? Yes. you should have this instability. This whole story, I mean, I should emphasize, we're still working in the Stokesian regime. Further, if you have particles, even in the isotropic phase, if you put on a flow and align them, then pushers push the flow in the direction which you already imposed, pullers pull against it. So a suspension of pushers is less viscous if they're alive than if they're dead, and they can even destabilize the isotropic state itself. Anyway, we had done this work, and I was walking past a talk at the APS March meeting in, I don't know, 2006 or 7, and I saw on the screen these pictures, and I saw something about our paper. And so I walked in, it was Mike giving a talk and saying, there are these, Simha and Ramaswamy have done this rather interesting piece of work. So this was the basis for a friendship which has endured. I didn't meet Mike actually that day. But anyway.
You were way in the back.
Yeah, no, and I had to go somewhere else. But probably the first sort of computer experiment that confirmed our ideas was these beautiful studies by Santillon and Mike Shelley a few years ago. And the first place where I saw, no, maybe the second place where I saw active turbulence. The first was the bacteria. So as I said, bulk active liquid crystals, Stokesian, are unstable and ultimately turbulent, and Zvonimir will doubtless tell you more about this spectacular dynamics. There's a great deal of work on this subject. I really cannot do any justice to it in this talk, especially if I want to talk about anything else. There's a nice review article specifically on active pneumatics. So now that closes the part of my talk having to do with the general complex dynamics of active systems. Our interest in the rest of this talk is first to say that we've been talking, if you think of self-propelled things, they have a nose and they go somewhere. But I've been telling you about active systems which are essentially apolar. How much of a difference does polarity make? And later, as you'll see, how much of a difference does inertia make? So let's first go back now, step away from this hydrodynamic picture and start looking at models based on little rules. You've got little motile objects which try to stay away from each other and try to line up with each other and maybe try to stay reasonably near each other. But basically, the aligning tendency and the tendency to follow your nose results at high densities and low noise in a transition from a randomly moving state to a coherently moving state or a flock. So this has an interesting history from the movie industry, but is generally known as the V-check model, in which they display a flocking phase transition. I'm telling you this because I want to tell you about the field theory that comes out of this. So if you take those ideas and coarse-grain them up into a continuum theory for a vector orientational order parameter, which is the local average of the unit vectors associated with the particles, then you have two important features. One, there's a tendency to align, which in this coarse-grained picture comes from a free energy functional which favors a given magnitude of P and disfavors gradients between P's, and in principle makes P align with concentration gradients, presumably pointing away from the high-density regions. P not only is an orientation, but is also a velocity. Therefore, it can advect itself. So P relaxes to equilibrium in a field given by this functional, but self-advects. P being also associated with particle motion carries the concentration. In principle, these two coefficients don't have to be the same. The straight dope on exactly why they don't have to be the same can be found in some papers by us. It's a result A of... Yes? Okay. Didn't agree. Okay. So this is the picture of a dry polar flock. What happens to this if you introduce fluid? By the way, this has many interesting consequences which I will not discuss, and our question was, but this is not a mechanical description. This is a coarse graining of an agent-based, rule-based description. What happens if all of this takes place in a medium where you have to worry about your momentum? Okay? So we worried about this actually quite a long time ago at this point. And our recent work on it is in a paper which you can find on the archive. So as I said, remember, first of all, the moment you introduce fluid, in the Stokesian regime, the instability that I told you about a few slides ago kicks right in, but in a form modified by polar effects. And some of those polar effects have been discussed by some of our friends. But supposing you want to include polarity and you want to venture timidly beyond the Stokesian regime. Okay, I'm not claiming that we can describe this system, but at least introduce inertia and see what can happen. Okay, so if you do that, then at leading order in wave number, what you find is an interesting sound wave-like spectrum due to the coupled dynamics of orientation, concentration, and hydrodynamic velocity field. Okay, the dispersion, these curves represent the speed of the waves. The radius vector from the origin to a point on the curve tells you about the speed of the wave in that direction. So you have coupling of splay and concentration, and bend and vorticity. But this was all, the only analysis we did back then was to leading, that is linear order in wave number. The question is, what is the full story? And it turns out the full story, although technically complicated, is rather interesting. So the complete hydrodynamics of a velocity field and a polar orientation field looks like this. So you've got terms that you're familiar with, and you have stresses coming from conventional orientational ordering as in equilibrium liquid crystals, and you have a new bit of the stress, which is the active stress. So that new bit is that if you have a local polarization P, you have a local deviatoric stress or local uniaxial stress bilinear in P. The conventional stresses coming from the free energy functional I will not dwell on. The polarization field is rotated and advected and flow aligned, relaxes to equilibrium, and can advect itself. So putting these together, you get a fairly forbidding set of equations. What we're going to do is we're going to simplify drastically. We're going to keep the simplest form of the active stress, keeping only the apolar piece. We're going to keep the simplest form of the equilibrium reactive stresses. We're not going to worry about the concentration field, which is a potentially serious omission. And so what we'll be doing is looking at the coupled dynamics of the polar order parameter and the hydrodynamic velocity field. The polar order parameter advects itself. The hydrodynamic velocity field also advects it. It interacts, it can be aligned and it can be rotated, and it relaxes. And the velocity field obeys a modified Navier-Stokes equation containing active and passive stresses that I described on the previous slide. Okay. What we've done is the fact that the orientational order has a polarity enters here only through this term. In principle, we can put in the other terms that we had. It complicates the story without making it necessarily that much more interesting. Okay, and the case that turns out to be really interesting is the case of extensile or pusher swimmers. And the other point I want to make is that activity enters in two places. One is through the active stress, and the other is through motility, which makes the object advect itself. In principle, in a coarse-grained description, since I'm not Mike, I have the luxury of saying that these are two independent parameters. Exactly how they relate to a microscopic description is complicated because you can imagine swimmers whose main propulsion mechanism doesn't come from a force dipole, but which nonetheless have a force dipole. So that's my sort of apologia for why I'm going to treat these two as independent parameters. Okay? What did I do? That's okay. Yeah. There are dimensionless quantities which are important. First of all, familiar from conventional liquid crystal physics is this combination, which can be thought of as the ratio of the diffusivities for the director and for vorticity, or equivalently can be thought of as the ratio of the nematic elastic constant, which has units of force in 3 dimensions, to Purcell's force scale for a viscous fluid. Mu squared over rho is that scale. This one, which is essentially the same but has the orientational kinetic coefficient instead, but that is generally of order 1 over the viscosity. These two numbers in molecular or colloidal liquid crystals are known to be really minute. Okay? And what that means basically is that if you have a standard orientable suspension, vorticity diffuses way faster than orientation. Familiar. The important new non-dimensional number is a comparison of two kinds of quantities which you can think of as something like active stresses. Sigma 0 is the typical scale of the force dipole stresses. And there's this term, which please note has a mass. This is rho. This is not the solute concentration. This is the total mass density of the system. So you've got this non-dimensional this ratio of two stress-like things, something like a ratio of inertia motility to active stress, and that will play a crucial role. So what you can do is you can take these equations and you can consider a completely aligned state and perturb it and see what happens. And what you find most interestingly is if you look in 3 dimensions at modes that interpolate between twist and bend, you find the frequency has a piece proportional to q and proportional to q squared. You can expand it further. The bit that goes as q has a piece just coming from the self-propelling speed, but has a contribution coming from the non-dimensional parameter that I just defined. Okay, 1 plus lambda is a flow alignment parameter. Basically, there's a value of r of order unity where this quantity inside the square bracket, inside the square root, changes sign. So if r is too small, for example, supposing it is a totally apolar system, then this would be negative, and you would have an extremely rapidly growing instability at small wave number. But if r is appreciable, you can escape this instability and have this thing be positive, and therefore its square root be real. The second part is imagine that r is large enough that you avert this instability. At order q squared, you can still have an instability, which I won't labor it. I'll just tell you that this bit will give you an instability. So basically what that means is that if you plot the imaginary part of the frequency, that is the growth or decay rate, as a function of wave number, if our non-dimensional Reynolds-like number is small, you have an instability which seems to go to a non-zero value at zero wave number, but in fact, at wave numbers small compared to the scale where the active waves inertia dominates over viscosity, goes down, and you have a growth rate of order q. As you increase r, eventually for large enough r, you escape instability altogether, but in between, interestingly, you have a regime where the growth rate is quadratic in wave number and stable at large wave numbers. So really, you have r small instability with growth rate of order q, r large instability with growth rate of order q squared. This instability at small r is essentially, if you didn't have inertia at all, this would be the instability that patches to the classic Stokesian instability with a growth rate, with a non-zero growth rate, a small wave number, growth rate of order active stress over viscosity. Okay? So if you like, what we thought of as the generic instability of a Stokesian active liquid crystal is actually the unstable end of a much richer behavior. And as you increase this number, whose name I hesitate to call it Reynolds, but as you increase R, you can actually enter a regime where you're either totally stable or unstable, but much more softly unstable. As a function of R, and this is that parameter which I told you, ratio of pneumatic elastic constant to Purcell's force scale. If this number is actually 1, the q squared regime vanishes. But for any other value of this parameter, you have a q squared unstable region, both if the parameter is small, as in conventional systems, or very large, as in systems that I don't know. So basically, at large R, you have a stable flock. Generically, you go through a q squared unstable region and a q unstable region. That's the linear stability analysis picture. Now let's ask if the real dynamics of the system bears this out. And so we've done numerical simulations in 2 and 3 dimensions. I am professionally not at all a numerical person. My colleagues, whose pictures I showed you earlier, Ryan and Prasad and Navdeep, did this. The 3-dimensional simulations are a very modest size. The 2-dimensional are somewhat more respectable. And these are the technical details of how it was done.
Will you remind us what R is again?
Yes.
It doesn't hurt even if you have...
Yeah, absolutely. Okay. So there is sigma 0 can be thought of as the force dipole density, force dipole strength times mean concentration of active particles. V0 is the self-propulsion speed. So it's a ratio of something that looks like an inertial stress associated with the self-propelling speed to a force dipole based stress. If sigma 0, if you have a sort of essentially viscous swimmer, sigma 0 should just be the viscous stress at the particle scale, and then this thing will actually become the Reynolds number at the particle scale. But you could imagine applying this idea somewhat generously to larger swimmers, and then it's not so obvious that this is just the Reynolds number at the particle scale. Yeah, okay. I'm almost done. So if you watch numerically the order Q unstable region, what you find is it dissolves into a sort of paroxysm of integer strength defects. Remember, these are polar systems. The defects have integer strength. And so what you really get is three-dimensional hedgehogs and hyperbolic hedgehogs, of which you're seeing a section here. If on the other, if on the other hand you sit in the region where the uniform state in the linear theory was unstable but to the growth rate of order wave number squared, what you get is it sort of makes its own noise but doesn't destroy itself. So it would appear that the regime that is linearly unstable but with a slow growth rate is actually ultimately in a time average sense an ordered state. So it looks like this is what a typical configuration looks like. And so we suggest that this state at somewhat larger r is actually an ordered state. If you like, what we're arguing is that this is defect turbulence and this is phase turbulence. Okay? We haven't done a formal analysis to show this. What we have done is to measure the orientational order parameter. So you've got your particles, you've got your orientation field P, you do its macroscopic time average and look at it as a function of R. And despite the limited range of our numerics, what you see is a quite clear onset as you increase R in the region around R equals 1, from a state with average P equal to 0 to a state with average P clearly non-zero. If you measure the orientational correlation function, as you increase R towards 1, the correlation function decays more and more slowly with some structure here which we don't understand. You can, again, this is not data over huge decades, but you can collapse such data as we have onto a single curve by choosing a length scale either from an exponential fit or from the area under the curve, doesn't really matter. And if you plot that length or the inverse of that length against R or 1 over R, you can see that there seems to be a fairly systematic increase in that length as you approach R equals around 1. Again, not a huge range of increase in R in the correlation length, but there it is. So there seems to be a flocking transition from a highly noisy defect-ridden state to a noisy but still ordered state. So that's the major finding here. So I will actually summarize. We have done measurements of things like the nature of turbulence. I'll say a little bit about it. Basically, what we found, I guess, actually is 3 kinds of active turbulence. The one I showed you at the beginning, driven by motile defects, and 2 kinds of turbulence in wet systems. In the dry systems, the motility of the +1/2 defects drives melting and some kind of chaotic state. The melting is reentrant. In a flock in fluid, inertia seems to help stabilize the system. Somebody asked about the nonlinearity. Essentially, it's the P dot grad P nonlinearity that is the important one. In fact, we even checked by suppressing U dot grad U and didn't make a serious difference. You can also measure characteristic local Reynolds numbers on a given scale by looking at velocity differences, hydrodynamic velocity field differences, and those numbers are small. So we've argued that the generic instability of active liquid crystals is actually the defect turbulent phase of a larger phase diagram. There seems to be a non-equilibrium phase transition from defect to an ordered phase turbulence. Among the things we're really interested in is the following. So now, if you go back, I have 1 minute, which is good. Let's say if you go back here, if you look at this growth rate picture, you can say that this defines a characteristic wave number scale, and on wave numbers much smaller than this correspond to the long wavelength theory. You can say, look, I won't look at any of the stuff over here. Supposing this was Kuromoto-Sierpinski, I would say I'll take all the modes from here and treat them as the fast modes and ask for the effective theory for the slow modes here. What is that effective theory? It's a great project, but it's a daunting one. We haven't done it. And that would tell you what the effective stochastic PDE governing the long wavelength system behavior is. if you look over here, on the other hand, if you make measurements like turbulence measurements, if you measure energy spectrum for the velocity field or the orientation field, you find, broad spectra, but we've not done a serious analysis, and by no means have we done a serious attempt to explain them. But they're there. I can show them to you if you like. And we have certainly not tried to construct fluxes and figure out what they do. So these are all things that, that remain to be done. We don't have the effective long wavelength theory. Is there a cascade? Any of these things. And in both these, it would be really interesting to have experiments. The experiments in the dry active pneumatic case are rather challenging because those systems tend to be dominated by the coupled dynamics of the orientation and the number density, and we have neglected the number density. So it might be easier to do it in direct numerical studies of a active pneumatic with birth and death, or a PDE. So with that, I'll stop. Thank you for your attention.
The data from the previous graph simulations, right?
Yes. Yeah.
Yeah.
Could you say a bit more what you think would be an experimental setup?
So I know that people are now starting to study swimmers with finite inertia, like Daphne Klotza, for instance. So though, if you can make, I know the trouble is those are fairly big objects. I'm not really sure, but it's, I'll be shameless and say it's a challenge to the ingenuity of the experimenter to figure out a good system. But probably the first thing to do is to do, for example, if one took the kinds of studies that you did 10, 15 years ago and do them on particles with a bit of inertia, where there's more polar particles with a well-defined mass density. It might already be interesting.
Actually, I would like to ask a question. So, given that we are like very broad audience
Yes.
from different
Yes.
fields,
Yes.
for example, I'm from astrophysics.
Right.
Could you a little bit elaborate on what possible applications to real life do we have for this kind of special fluids?
Okay. So the part of for many people in this field, the motivation actually came not at these length scales, but at cellular or subcellular length scales, in trying to understand the mechanics of a cell. If you take even one cell, it's full of filaments and motors. So that one cell, or even the one nucleus, as Mike pointed out, is an active object. If you want to understand what makes it sit, spread, stretch, divide, all those things, the mechanics you have to do is the mechanics of a system in this state of constantly eating energy. So there's that. Certainly, people hope to devise artificial systems in which you can control the activity, maybe by light, maybe by other fields, in such a way that you've got objects that are autonomously movable, and then you try to direct their motion by various means to deliver various things. People claim these things. I don't know whether it has gone beyond statements to funding agencies and in the last paragraphs of review articles. Our own motivation actually came because of my general interest in liquid crystals. And I had seen the flocking literature. I said, wait a second, we should do hydrodynamics of flocks in fluid. And very interestingly, as an illustration of universality, exactly the equations we wrote down trying to think about oriented states of organisms reappeared a few years later in the Curie Institute people's work when they were trying to describe something inside one cell. So I think there's a nice lesson there. But I think the major interest, but so certainly cell biology is probably the most likely place. And this framework has certainly been used there, not only in cells, but in tissue and so forth.
At some point in one of the initial slides, you mentioned active quantum method. What did you mean?
Okay, so let me tell you, I don't even need the slide there. I can show you the slide just to show you yeah. So it wasn't a completely random statement. Just a moment.
I never meant.
No, I'll show you. Let me just go to that picture. I just want the picture in front of me because I can point to something. Sorry?
I think there's a refractory period.
Yeah. No, it's particularly if there are slides with movies, then it's very refractory. Yeah. So what I was saying here is the following. So if you have a 2D system, say a 2D electron gas, and you rain something on it, microwaves on it, and then you ask, in that state of a sustained throughput of energy, what dynamical equations will you write down, let us say, for charges and currents in that system? So people have found in 2D electron gases suffused with microwaves, they found these things called the zero resistance and negative resistance states. Those states were nothing but flocking of electron currents because the state of zero current was linearly unstable. They even analyzed those experiments using Toner 2 style flocking models, modified by the presence of a magnetic field and by Coulomb interaction.
So these were quantum electrons, not classical.
Well, it is a real system, and therefore it is real electrons. Yeah.
I'm trying to understand this. Orientation is just a vector, right?
Yes.
It's an angle. So I don't understand how.
Use the microphone.
Which one?
What?
Yeah, sorry.
Yes.
And you get in Navier-Stokes equation acceleration proportional to orientation, and this I'm
No. So, okay, let me be more precise. If you have a collection of oriented objects, each of which has a built-in force dipole on it,
okay.
then you will get a local stress bilinear in the orientation vector.
Yeah, but it has this two direction the same, namely
Yes.
it doesn't know which way to go. It
Exactly,
knows
and that's
which
why you
line.
get a stress.
Okay, so it
So
must
it's
be
pi sigma ij proportional to pi
so it must be
pj.
divergence of this stress which would give you
Конечно.
acceleration. Okay.
Yes.
Okay, so I think we're out of time. It's very interesting for further discussion, maybe in the discussion section.
I will be talking today about data simulation. So data simulation, and also known as filtering in its sequential form, is a framework for state estimation and prediction in dynamical systems that is used indispensably in real-world forecasting applications such as weather forecasting. So the general setup here is that one has a characterization of the state of a dynamical system through some probability distribution, which is advanced forward in time by means of some model, some kind of dynamical model. Let's say like a Navier-Stokes equations would be Navier-Stokes solver, and it produces some probability distribution later in time, and then at some point there is a measurement that is made, and that probability distribution is updated to a new distribution about the state, and the measurement here usually is not, it's a partial measurement in the sense that one doesn't have access to all the degrees of freedom of the system, and essentially by an application of Bayes' theorem, this yields an updated probability distribution. And this procedure is repeated, and the idea here is that even starting from a fairly uncertain distribution in the beginning, after several iterations of this step, this procedure, one can get a very highly accurate characterization about the state of the system. So, as I said before, this is used indispensably in many techniques involving turbulence. Weather forecasting is one example. It started in the work of Kalman. Now, conceptually, at least, as a qualitative picture, the data simulation procedure resembles some aspects of another highly successful theory in modern science, namely quantum mechanics. So in quantum mechanics, one characterizes the state of a system by something called the density operator. I will describe this in more detail later on. And there is a dynamical flow, so there is some unitary dynamics by the Heisenberg evolution operator that advances this density operator or density matrix between measurements. Now, when one makes a quantum mechanical measurement, there is a procedure analogous to the Bayesian update rule, which also is known as a wave function collapse, that updates the state, the quantum mechanical state, to a new state by some type of projective dynamics, or some kind of projection of the state. So these two, this can be repeated in time. So these two procedures shown here have some qualitative aspects in common. What I would like to talk about today is whether we can actually turn this into a precise data simulation framework for classical complex system, utilizing basically the axioms and the mathematical structure of quantum mechanics. And this will be done using some ideas from dynamical systems theory, in particular Koopman operators, And one nice outcome of this is that the resulting framework is also very amenable to data-driven implementation using machine learning techniques. I will talk about that a little bit. Okay, so I want to start by reviewing very briefly the axioms on quantum mechanics. So the essential ingredient of a quantum mechanical system is some Hilbert space. And that particular Hilbert space depends wildly, very strongly on the application. It could be a finite dimensional space if you're dealing with something like a spin system, an infinite dimensional space if you have something like a harmonic oscillator. But once that space is identified, then the state of a quantum mechanical system is a operator on that Hilbert space, which you can think of as some kind of non-commutative generalization of a probability measure in statistics, non-commutative because operators on Hilbert spaces are generally non-commutative objects. And it is normalized in the sense that it has unit trace. So you can think of trace as replacing the notion of an expectation value of a probability measure. The observables of the system are self-adjoint operators on the Hilbert space. Now, between measurements, as I was saying before, there is a unitary evolution by the Heisenberg operators, and that depends, again, on the particular quantum system, but basically they evolve densities, operators to density operators at later times. And the observables, they're self-adjoint operators, and so quantum mechanics gives us an axiom to characterize the probability of experiments yielding particular outcomes. So here, the central object is the so-called spectral measure associated with a quantum mechanical observable. You can think of it, again, as some kind of operator theoretic or non-commutative generalization of a Fourier power spectrum, which is uniquely associated to each quantum mechanical observables. And basically, the statement here is that all possible results of a physical measurement are necessarily elements of the spectrum of that operator, which is a subset of the real numbers, because it's a self-adjoint operator. And there is a specific formula that gives you basically the probabilities for physical experiments to yield particular outcomes when you're dealing with a particular observable and when your quantum mechanical system is in a specific state. And finally, there is an axiom which is the analog of the Bayesian update rule, which tells you how to update the state of the system when an actual measurement is made. This is some type of projective dynamics that depends on the spectral measure of the observable being measured. So this is basically the standard formulation of quantum mechanics as developed by Dirac and von Neumann. Now we want to connect this with data simulation, so statistical inference, in essence, of a classical dynamical system. And we're going to do this using ideas from operator theoretic ergodic theory, in particular Koopman operators. So what we consider in general, that we have some classical dynamical system that evolves in some state space. This can be, again, pretty general. If you have a system of ODEs, this could be RD, if you have decoupled ODEs, or if you have a PD, this could be a function space itself. And on the, sorry, so on our state space, we have some dynamical evolution map that you can think of as the solutions of your ODEs, if that's what you're dealing with. This is in general a nonlinear object. But for this system, we can identify naturally a Hilbert space if we have if the system is measure preserving. So there is some notion of statistical equilibrium. So it has an invariant probability measure mu, and there is a natural Hilbert space which is preserved by the dynamics, namely the L2 space of functions, real or complex valued functions, on the state space. So these are classical observables which are square integrable. And on that space, there is a unitary operator acting called the Koopman operator of the dynamical system. So it acts on observables, on classical observables, by composing them with a dynamical flow in this manner. So that's a unitary linear operator. And we're going to assume that we're doing data simulation, measuring at every step some again, a classical observable of the system, which we're going to take to be a bounded function. Okay, so now we have essentially the main ingredients to just transcribe the quantum mechanical axioms and build a data simulation framework from those. So we're going to treat, even though the state of, keep making mistakes here, state of a classical system is typically a point in its state space, in data simulation, we're interested in the statistical state of a system. And we're going to describe it here with a density matrix, a density operator, exactly as in quantum mechanics, which will act on the L2 space of the dynamical system. We're going to, again, consider, quote, quantum mechanical observables as self-adjoint operators on L2, but note that if we have a classical observable, so a function in L2, we can associate to it an operator that acts on other functions on L2 by multiplication. This is familiar also from quantum mechanics when you have something like the position operator, which just multiplies the wave function by the position. So we're building basically quantum mechanical observables from classical observables in this manner. And now the natural analog now for evolution that replaces the Heisenberg operator in quantum mechanics is the Koopman operator. So we can use the Koopman operator to advance the density operator in times. So that gives us a way of making forward evolution between measurements of the system. And we also have a similar axiom as in basically, well, we have the spectral decomposition of self-adjoint operators, and again, we can use that to state that whatever measurements we're going to take are going to lie in the spectrum of our observable, and if we happen to deal with a classical observable after doing classical data simulation of a classical system, well, the spectrum of a multiplication operator is nothing but the range of the function that we're measuring. So this is consistent. Okay. So, and then there is a procedure that allows us to compute probabilities. So this is an intrinsically probabilistic framework. It operates on probability distributions intrinsically. Its output, it's going to be probabilities of events to take place. And there's a simple formula that allows us to compute spectral measures and probabilities, specifically when we're dealing with multiplication operators. So finally, there is the update rule, which replaces as before, the Bayesian update step by projective dynamics acting on the density operator. So essentially, using this Koopman language, what we've been able to do is just create, at least on paper, a procedure that for data simulation that more or less transcribes in an identical manner the axioms of quantum mechanics. And the question one might ask is, why would you want to do that? Well, I think on the one hand, this is maybe intrinsically interesting that somehow you are mapping a partially observed classical dynamical system for which you have uncertain knowledge of the state into a quantum system and using that for purposes of inference, but also the added flexibility that the fact that we have put the problem of data simulation in a bigger space of these operators and quantum mechanical observables is actually quite useful for the purposes of doing empirical approximations or realizations of this scheme, because now everything is formulated in terms of linear operators. We have a lot of machinery to do approximation of linear operators, and this can naturally address some problems that one encounters in classical data assimilation, with, for example, non-Gaussian behaviors and so on. So I want to give a very quick example before I go into that of how this scheme behaves. So in particular, just in the context of an oscillator, just a harmonic oscillator, which as a dynamical system, you can describe it as a rotation on a circle with some frequency. So as I was saying, everything here is done based on linear operators, and you can represent these operators by matrices. I'm just showing these formulas for this example just to show you that one can write them down. But what you can do now is just run a very simple experiment on your laptop, where what we're going to assimilate is a binary function, so a function that takes either the value 0 or 1 somewhere on the circle. It's like essentially flipping a coin. And yes, there is some kind of underlying state. We're going to have some underlying realization of the dynamics that we don't know. We're going to start from some, at initial time, from some basically uniform, some uninformative density operator for our quantum state, and then we're going to make measurements. So measurements here are indicated by these asterisks, and the blue line denotes the probability that we predict for the value of the observable. The green line is the true trajectory. And so what you can see is that after a few trials, essentially, this system locks on very accurately and predicts this binary observable. Initially, it's not doing so well, but after a few sequential observations have been made, it locks on to the true evolution pretty well. And you can make this more challenging by modifying your assimilated observable to only take the value of 1 for short amounts of time, creating this sort of spiky signal. And eventually, again, after a few measurements, it's able to lock onto it pretty well. So this is just a basic example. We have, in recent years, we have been working extensively on developing machine learning-based methodology for approximating Koopman operators. I don't have time to go over that here, but I'll be happy to talk about it later if anyone is interested. But basically, the idea is that we create, using kernel algorithm, sort of customized Fourier basis for our L2 space of our dynamical system, and then use this basis to represent linear operators as matrices in a controlled manner that can be refined as we collect more and more data. So using this framework, I just want to show one example for a system that was mentioned also in the previous talk, namely the Lorentz 63 system, which has chaotic dynamics. And one of the challenges here is that due to the nonlinearity of the dynamics, you have highly non-Gaussian statistics. In fact, all the probability measures are supported on this fractal attractor that Fabian showed also at his talk. That makes it very challenging from the point of view of designing a data simulation scheme. This is just some example of our basis functions that the kernel algorithms produce for the Lorentz attractor. These are mathematically well-defined. You can think of some type of Fourier basis for the Lorentz attractor that you can use to represent other operators and solve different problems. So this is the result. The result of doing data simulation with the scheme of the x-coordinate of the Lorentz attractor, basically observing only the x-coordinate. This is time here. Colors show logarithms of predicted probability density, and the red line is the true signal. So we start again from some uninformative state, and then as we make measurements, this basically our predicted probability collapses down to something that over time, even though initially we make some mistakes, there is some bimodality here in the distributions, over time it improves and it tracks the true state of the Lorentz 63 system in a fairly accurate manner. I should say that the observations here are separated by about 1 Lyapunov time scale, so there is some increase of uncertainty in between measurements. So yes, for the 1 minute, I just want to, before ending this talk, I want to mention one real-world example. This is in work with Joanna Slawinska, where it's a real-world example, and turbulence in some level, maybe not in necessarily what we have been talking about, at least today, plays a role. This is the El Niño Southern Oscillation, or ENSO, in the climate system. Here we are, this is preliminary work where we have applied this scheme to assimilate this phenomenon in a climate model. So the El Nino Southern Oscillation, as the word might say, is an oscillatory pattern that appears in the tropical equatorial Pacific, and it manifests in terms of the El Nino events, which are basically warm sea surface temperature anomalies in the eastern equatorial Pacific, and cold events, these are the so-called La Nina events, where there's sort of the opposite situation. And what we're doing here, we're designing an experiment where we measure these so-called Nino indices. These are averaged SST, sea surface temperature values, in different parts of the Pacific. So you could consider this as a data simulation experiment with an extremely coarse observational network, consisting of only like 4 grid points in these boxes. And what we're trying to infer from that is one of these indices. It's called the Nino 3.4 index, which is representative of the El Nino phenomenon. So this is the output of this. This is showing assimilations basically happening on a monthly basis. And in the difference panel, there, again, we're showing in colors the log of the predicted probability. And going downwards in the panel, you have increasing lead time. So basically, you start from a situation which is highly certain at early times, and naturally, uncertainty increases. These probability distributions become broader and broader until eventually, at some point, predictability is lost. But it seems to be, working at least in these preliminary results in a reasonably good manner, providing a meaningful representation of uncertainty. So I'll leave these conclusion slides here, and thank you very much.